Hi everybody, sorry about the delay there. Let's get started with today's 121 lecture. Welcome back to Chem 121. Agenda items, there's all sorts of stuff due tonight. Last call for quiz 7 is tonight. Make sure you get that in by the deadline or else it closes. Quiz number 8 and lab worksheet number 4 are due today, but that's a soft deadline. The deadline for that closing is tomorrow. So there's a lot to do. And we're going to finish Chapter 9 today, probably, so that quiz will be coming out soon. I believe that's the last quiz. There's only 9 quizzes in this class. I don't have a Chapter 10 quiz. That just shows up on Exam 2. So let's get started. We're going to start today by talking about a concept called equilibrium. And in order to do that, I'm reminded I need to get something here. I'm trying to find the simulation here. Let me see if it works, because I do need this to go. Sorry, just a moment. I do not see it here, interestingly enough. It may not exist at the moment, which is really unfortunate because I could have used it. Oh, I have to check a different button. Did it appear now? Here it is. Let me see if this works. Apologies for the delay. There we go. Okay. So now what I need to do is capture this. All right. So what I'm going to put on the screen, this is going to look a little strange at first. All right. So I have this sort of setup here, and you can see that what we've got going on looks kind of like the energy diagram that we were talking about. So like I could have an activation energy and a starting where my reactants are and where my products are. And I can, the blue curve looks like the energy diagram we drew yesterday. Now what I'm going to do is I'm going to put a bunch of reactants in the chamber here. I'm going to put in 500. Boop. Oh. There we go. There they go. And now you're going to see that they're going to react. And you would think, well, okay, everything is going to eventually just turn into products, right? Maybe 500 was too big. Hold on. Let's do 100. There we go. So there's some reactants going. You would think, okay, everything's going to turn into products, but what do you notice about the products over there? They have energy, right? They're bouncing around, and some of them are even turning back into reactants, as you can see. So even though it's far easier for my molecules to go in the product's direction here, and then they would get trapped down here at the bottom, they still have enough energy to bounce back and become reactants, right? Now, over time, you could see that this is going to slowly go down and that this number is going to slowly go up. The amount of A reactants is going to decrease and the amount of B products is going to go up. But is it ever going to reach 0 and 100? No, it's going to settle out on some number. And so what I'm going to do is I'm going to hit this button here. And we'll just pause it intermittently. So we'll say that at the start it was about 50-50. And we're going to come back and check on this throughout the lecture. Because what's going on here, I'm going to let it run in the background here. What's going on is there is a phenomenon called equilibrium at play. And this phenomenon governs how all reactions work. It also means that we've sort of been lying to you about how chemistry behaves up till this point. So we have said that all along we have worked on the assumption that reactions completely consume the reactants, only the products are left behind, and then that's it. We're stuck with the products. The products are what you get forever. But in reality, that's not the case. For this reaction specifically, HCl and H2O react to form H3O plus and Cl minus. So this is the dissociation of a strong acid. This reaction does actually behave as we described. The HCl dissociates 100%. If I were to look into the container for how much HCl is available, I would find that there's absolutely no HCl there. It is completely dissociated. And this is by far the exception rather than the rule. For many, many, many circumstances, when we do a reaction, we end up with a little bit of reactants and a little bit of products, and not the entirety of both. Now, how much do we end up with? Well, it depends on what we're reacting. In this case, you might be surprised to find that for acetic acid and water, this is just vinegar. Vinegar is quite tart, right? So it should be really acidic. And yet only about 0.5% of it actually dissociates. The remainder just stays vinegar. This would be the tart part that you taste, is this right here, due to the acid. Now, why is this the case? Why does vinegar not react with water as effectively as HCl does? There are a bunch of reasons for this, but we're going to summarize all of those reasons together in a phenomenon called equilibrium. And equilibrium works on the premise that if a reaction can go forward and turn from reactants into products, what's stopping it from going backward? Why can't the products turn back into reactants? Maybe it's a little bit more difficult. Maybe it's similar to this diagram that's hiding. There we go. Oh, my diagram disappeared. Is it this one? Yeah, there we go. What's stopping my products, even though they're more stable, maybe they do have enough energy, and you can see that some of them are starting to turn back, right? All right, so now it's been 140 seconds, and we're at about 1/3 and 2/3, so 33 and 66. And you're going to notice that as we keep coming back to this, it's going to be more or less constant over time. So for every reaction, the possibility that our reaction can go in reverse exists. So if this is my forward reaction where my vinegar dissociates into my acid and then this acetate ion, what if these two bumped into each other? Well, they could react and I get my vinegar back, right? The way that we write this is that we write the reaction in the forward notation, but then we just write a double arrow. So this forward arrow and this backward arrow indicate that both directions are possible. And technically speaking, for nearly all of the reactions that we've been exploring, we should have been writing double arrows. But we didn't, and that's fine. Now, though, we'll address that with, oh, this reaction is reversible, and we will indicate that with the double arrow. If you don't see the double arrow, assume that it's not reversible, because there are some reactions out there that aren't reversible. There are just very few of them. Now, for a reversible reaction, both the forward and reverse reactions occur at the same time. And you can see that in action right here. Oh, it's paused because the window's minimized. But you can see that A is turning into B. Every time a green marble passes the midpoint, it turns red. But every time a red marble passes the midpoint, it turns green. So I have things that are turning back and forth. So here a bunch of things just turn into products. There goes some more products. Here comes some reactants back. And we're very slowly equilibrating to some number. What that number is, I actually don't know. I just sort of set this up to see what would happen. Now, so, okay, if both of our reactions are going forward and backward, one reaction, the forward reaction, makes products. But the reverse reaction can turn those products back into reactants. And at some point, the amount of products and reactants that you have remains constant. Now, they won't equalize, because as you've seen in this diagram here, they're not equal, right? I have way more products than I do reactants. But what we're looking for is for the amounts that are present to be roughly the same over time. And if I keep doing... Oh, I have to actually maximize it again. That's okay. And as we keep checking in on this, we will find that we have eventually reached the point where we have more or less the same amount of stuff over time per side. So, like, if side A just kind of hovers around 25 to 30 here, now it's going down as soon as I open it. But if it hovers around 25 and doesn't increase or decrease relatively that much, because it's dynamic, and side B hovers around 70 or 75 or so, if the amounts aren't changing that much, we've reached a pretty regular state. The number that are going left is equal to the number that are coming back from the right at any given time. And we would call that state equilibrium. And you can see that you just sort of naturally reach an equilibrium. Now, why is it 25 versus 75 here? It has to do with where I put these elevations, right? If I were to pull this... Oops, you can't see my cursor. If I was to pull this guy down and make a well, I would get more stuff stuck over here, right? So it's harder for things to escape this deeper well, so I'm going to have more products relative to reactants. If I made them the same height, it should be 50-50, right? If I just shove them all the way up to the top, it should be 50-50. If I make this offset from the diagram, I get an equilibrium. And the equilibrium is pushed in the direction of the side that is lower in energy. This is why we did all these energy diagrams yesterday, so I could show you this graph, so that we could conceptualize equilibrium. And we'll keep checking back on it. I don't think it will change much from this range, so like 25 plus or minus 5 seems to be where equilibrium is. So we'll just let it keep going. But the state at which we reach the same amount of products over time and the same amount of reactants over time. Note that the products and reactants themselves will have different amounts, but within each side, products or reactants, that amount will be constant. That situation is called equilibrium. And I have a bunch of graphs to show you this. So here's an example. The reaction that I'm going to show you on the screen is hydrogen plus iodine makes HI. High. I don't know why I looked at the computer when I said high. Like I was trying to look at you, the student, but when I react these two things together, they occur when one of these smaller white molecules bonks into one of these larger purple molecules. And you can see that I have them dispersed in my container. when I say go, as if I can do that and let reactants just start reacting on the snap of my fingers, what I observe is that I will slowly accumulate HI. And that whenever my H2 and I2 bonk into each other, they can react. But if an HI bonks into another HI, they could decompose back into the starting materials. That's just a matter of, do I have enough of it present for these to find each other? And over time, I will accumulate more and more HI, but at some point, the amount of HI that I make will be replaced by H2 and I2 that are made when two HIs that were just made get decomposed somewhere else. And I will be forming them and decomposing them at the same speed. And past that point, the amount of HI in the solution here would not increase. So here you can see that in B you can see there's more than A, so we're not at equilibrium. In C you could see there's more than B, so we're not at equilibrium. But at D you can see that there's the same amount as C, so we must be at equilibrium. Now, did the reaction just stop going? No. The 8 HI that are here in C are not the same HI that are here in D. Some of them probably broke down into H's and I's, and other new HI was formed. But the relative amounts are the same. So once we reach the same amount, we're at chemical equilibrium. This link is actually what I'm showing you right now. So that's this guy here. Let's go back and check on it. And you'll see that we have reached more or less the same number. Every time I check back on it, the numbers are roughly the same, right? It's about 25 and it's about 75. So we've reached equilibrium. What I'm going to do now is I'm going to hit clear. We're going to reset everything. And I'm going to make this like super... We're going to do something like this. And what I want you to try and do, if I can grab this... Can I not load? Oh, probably because it's too high. There we go. I'm going to do something like this. What do you think the result's going to be? Actually, you know what? Hold on. Let me change this up. We're going to do this. What do you think the result is going to be for this when this reaches equilibrium? We're going to put 100 in here again. And so I'm going to hit start, and all 100 are going to get dumped over here. And then what I'm going to do is I'm going to add a little bit of heat so that I speed up the reaction. So this will get to equilibrium a little faster. Because we said adding heat increases the reaction speed, right? So if I add enough heat, my molecules will move faster, and there will be a larger percentage that make it over. And so we've already got a few that are over here. Now, where will this equilibrate to? How many will be up in this top corner? Will it just be 10 at most? Will it be 3 at most? We'll see. We'll come back to it. We'll let it reach equilibrium. But you should be able to predict that most of the stuff's going to stay on the left, right? So I have a very reactance-focused equilibrium. And that's possible too, depending on the conditions of the reaction. Here's another diagram to show amounts over time, and you can see that as I use up H2 and I2, the amounts that I have go down, and the amount of HI that I have goes up. But as I make more and more HI, I start to decompose it faster and faster and faster, until I get to this point where I'm decomposing it just as fast as I'm making it. Which is why the amounts of H2 and I2 aren't decreasing constantly. They start to smooth out again, too. Once I reach this point, I'm at equilibrium. Now, there's a bunch of terms for this. Chemical equilibrium, dynamic equilibrium. We're just going to call it chemical equilibrium, or even just equilibrium. But the concept is that at some point, reactions reach equilibrium, and the conditions of those reactions depend on what it is that you're reacting to get there and how much you're making. We're going to talk a little bit more about equilibrium in detail in just a second. But let's summarize what we've covered. It says some, but many reactions are reversible. Reactants convert to products, and products can revert back into reactants. For any equilibrium mixture, you're always going to have some reactants in your mixture. You're going to make products, but there will always be some reactants available, to some extent. And when we end up in a situation where the amount of products over time is constant, and the amount of reactants is constant over time, and the speed at which we are making products versus decomposing them back into reactants is equal, we have reached equilibrium. Now, consider the following with regards to equilibrium. What would happen if your body reached equilibrium? And all of the processes in your body that were making products were making equal amounts of reactants. And if your thought is, well, wouldn't you die? Yeah, you die. When you reach equilibrium, you're dead. Right? How do we stop equilibrium? Well, we keep feeding ourselves food, right? We provide reactants, and our body turns the reactants into products, and then we provide more reactants, and we keep doing this. So equilibrium is not this immutable thing. We can use it to our advantage. And that's actually going to be the premise behind the next section, which is Le Chatelier's principle, which is, how do I prevent a reaction from reaching equilibrium and making stuff that I want? So if I want this product, what do I do? And the answer is, you keep supplying reactants, and you just keep doing that. You remove the products and supply reactants, and it will keep going anyway. Now, we can look at the ratio of products to reactants in an equilibrium mixture and assign it a number. And the number that we're going to assign it is the equilibrium constant, K. Now, K is a really scary definition that we're not going to worry about. My slides are going to talk about it, but we're not going to worry about it. How do I define K? K is, if I have these coefficients right here, A, B, C, D, for reactants A, B, C, D, I figure out their concentrations and I raise these to these powers. This is just how K is defined, and I'm required to tell you that. But what we don't care about is what these numbers are, because we're not going to do this calculation. Instead, what we're going to do is we're going to do the following. What's on the top of the equation? Oh, it's C and D. Those are the products. What's on the bottom of the expression? Oh, that's A and B. Those are the reactants. And what we're going to do is we're going to think about K as a ratio of products to reactants. So we're going to look at the possible numbers that you can get for K, and just think about this conceptually. All right. Now, you can express concentrations in molarity. We're not going to actually do that. What we're going to instead do is we're going to visualize equilibrium like a seesaw. Now, you'll notice that my scale on the far left over there, or I'm sorry, on the far right, increasing is going down, and that's just based on the orientation that I drew this. I probably should have put the arrow on the other side now I think about it. But if I had exactly the same amount of reactants and products, I would have the same number divided by itself, right? So if products equal reactants, then products divided by reactants would equal 1. So if I have a reaction that has 50% reactants in it at equilibrium and 50% products, the equilibrium constant will have a value of 1. Okay, let's look at a different situation here. What if I have all products, sorry. I've consumed all of the reactants and there are only products. What's the maximum number that I can have? So if this is 100% and this is 0, products over reactants would equal the equilibrium constant, which would be 100% divided by 0%. What happens when you divide by 0? Well, you can't do that, right? You get a result that is infinitely large, but is undefined. So the largest theoretical equilibrium constant would be infinity. If all products were produced and there were 0 reactants total, you'd have an equilibrium constant that was infinitely large. Now, if I did the opposite here, here are all my reactants and I have 0 products, then I get this. So if I have a reaction that does not even go forward at all, then my equilibrium constant is just 0. So that tells us the following things. Oops, hold on. There we go. Oh, I guess we're writing in pink. There we go. For a reaction with some amount of products and some amount of reactants, if K equals 1, then we have 50% products and 50% reactants. If K is greater than 1, so in other words, from 1 to infinity, then there are more products and less reactants. And then finally, if K is less than 1, or in other words, from 0 to 1, then there are less products and more reactants. And that's what you need to know about K. Is that K is just the ratio, remember, K is the ratio of products divided by reactants. So what might happen is that you might be given a reaction with a value of K. And from that, you would be expected to say, oh, there are mostly reactants, or oh, there are mostly products. In Chapter 10, we're going to talk about acids, and acids have their own equilibrium constant. It turns out that most acids are weak acids, and they have very, very small equilibrium constants, which means that mostly they don't dissociate. There are mostly reactants. All right. Now, let's look at the reaction that we have from here. Now, it's probably changed a little bit, so let's see where we're at. There we go. Now, would you describe this reaction as having a large K or a small k? Would K be greater than 1 or less than 1? Go ahead and type what you think it is in the chat. Now, I don't know if people are like watching through playbacks or not, so I don't know if there's anybody actually live. But, oops, sorry, I'm clicking on the thing to see how many people are watching. But what you can see is that, well, there's very, very, very few products, because very few molecules can make it over this hill, right? A few of them do. So there's more reactants than products. So if we go back to this equation, where do we enter the bigger number? So if there are more reactants than products, what is a small number divided by a big number? Is that going to be bigger or less than 1? Less than 1. Yeah, there you go. So K will be less than 1 for that scenario. And that's totally okay, because we're learning. So you can look at the equilibrium constant of any reaction and then have an idea of it. So a reaction like this that I've been showing you, this would be in a reaction with a very small K. Excuse me. A large K would be where most of the stuff was on the right side instead, on the product side. All right. Remember when we talked about vinegar weight at the start? So I showed you this reaction. We'll go back to it real quick. I showed you this reaction and I said, wow, there's very, very, very little products here. What would the equilibrium constant be? And so we can actually show you that right now. So the value of K for this reaction is so tiny, if I were to write that in decimal notation, it would be this. So very, very little of this weak acid, acetic acid, dissociates into acetate and water. Or not water, but hydronium, H3O+. This is the acid part that we care about, so we're gonna talk about that in chapter 10. And so because its K value is so small, we must have mostly reactants. All right, so there's our summary that we had on the previous or not on the previous slide, but the whiteboard. So if K is between 0 and 1, there's mostly reactants. If K is bigger than 1, there are mostly products. If K is equal to 1, or really, really close to 1, there's about the same amount of both. All right, so I have put 3 reactions on the screen here. I just put random letters to represent, like, these things combine. And what I want you to do is tell me, what is there most of in each flask? So for flask number 1, so I'll number these. So this is number 1, number 2, number 3. Is there mostly A and B, or is there mostly C and D? Or is there roughly the same of both? Use the equilibrium constants to determine that. We'll go over the answers in about 5 minutes. 1 or 2 more minutes and we'll go over the answers. All right, so let's go over the answers here. So if for this first one, K is larger than 1, which means mostly products. So there's mostly C and D in this container. For this one, K is close to 1. It's I can't spell little. There we go. It's a little larger. So the intent was there's probably about 50-50, but there are going to be slightly more reactants, or I'm sorry, slightly more products than reactants. Down here, K is definitely smaller than 1. So it's going to be mostly reactants. And there you go. That's all there is to it. So from the equilibrium section, what I want you to get out of this is, what is equilibrium? Like, what happens? It's just eventually a reaction will settle at some amount, but that amount will not be the complete consumption of the reactants. We'll bring this guy back up here, and you'll notice we're still at equilibrium here. We still have about 6 or 7 that are up there at any given time. Now it's up to 10, but I bet some of them are going to fall back down soon, and it'll, yeah, there you go. So we've reached equilibrium. We get a few products here, and we have mostly reactants. So equilibrium is a state that exists. It occurs when the amount of products over time is relatively constant. The amount of reactants over time is relatively constant. And the speed at which we exchange back and forth is the same. So for every one that goes over here, I lose one back. And that's roughly the same, as you can see here. Then we've talked about the equilibrium constant, and for the equilibrium constant, we really just need to know these guidelines. If K is less than 1, mostly reactants. If K is greater than 1, mostly products. And if K is equal to 1, there's a mixture of 50-50 of both. If you have any questions, let me know in the chat. Happy to answer them. I'm going to skip over the calculation of equilibrium constants. You can read this if you'd like to. It's not difficult to calculate them, but I'm not going to test you on calculation of equilibrium constants. But there's the homework practice. Oops, sorry, I had the wrong button selected. There's the homework practice for this section. So again, your job is just going to be, tell me if equilibrium constant is big, small, or approximately 1, and what equilibrium means. All right, it's a little bit early, but rather than talk for 5 minutes and then have to take a break, we're going to take a break now. So we'll put this on the screen here. Where's my timer? There it is. I'll get the music back up. And I'll see you in about 10 minutes. So go grab some water. Go cool off. It's really hot out there. Be careful. Hi everybody, we're back. Get rid of the music here. Alright, so the last section in here is Le Chatelier's principle, but I want to say something really quickly about equilibrium and direction, because I refer to this on... I went and looked at the quiz just to make sure I wasn't asking you to calculate equilibrium constants. And there was one thing that I realized I hadn't mentioned, and this is just sort of a colloquialism that is used to describe equilibrium position. So, we already know that there are mostly products in both of these. There's more products than reactants in this one, and then this one there's mostly reactants. And so I'm putting a bunch of underlines on those to say where there's mostly stuff. Now, we can describe these as saying, okay, mostly products, mostly reactants, and then we'll say a little more products. But another thing that we can use to describe this is we could describe the position of equilibrium. And so the positions that we can pick are either left or right or middle. And we're just going to pick where we underlined. So here's where my equilibrium is on here. So for this reaction, the equilibrium is to the right. Whereas over here in this one, the equilibrium would be to the left. Left being towards reactants, right being towards the products. Now for this middle one, since there's only slightly more products, we would put it like right here. And so I'd say slightly right. So if you're close to 1, the equilibrium would be in the center. You could think of this as going back to our little seesaw. Where's the majority of the weight on the seesaw? Is it on the left side of the seesaw or the right side of the seesaw? Or is it balanced right on the fulcrum in the middle? So this is a term that is used, and it's used on the quiz. So make sure that you're aware of what left and right mean, because you'll be asked to select the position of the equilibrium based on data that I provide for you. All right. Oops. All right, let's do Le Chatelier's principle. Now, Le Chatelier's principle is a concept that involves us having a system at equilibrium, and then we're going to wreck it. We're going to change it. How does the system get back to equilibrium? What does it do? Now, obviously, a system will have a specific equilibrium that it tries to establish, and if you change what's in there, that will throw that off. Because if we're looking at this expression, K equals products over reactants, if I suddenly increase the number of products, then the value of K will change too. But this is called the equilibrium constant, which means that it's a constant and it doesn't change. So for a given reaction at a given temperature, at a specific temperature, K is constant. So if I don't change the temperature, I don't change K. If I change the products and reactants, K still remains the same. And so what will change instead are the products and the reactants. And we're actually going to see that in action in a few videos that I've got here. So let's suppose that I have this reaction, and K is, we'll say, 50. So my equilibrium is towards the right. There are mostly products. So I go and analyze the solution, and I say, okay, there's very little A, there's very little B, and there's lots of AB. And so what I'm going to do is I'm going to suddenly add B to the system. So now there's lots of B. And my ratio would be all thrown off, right? Because now there's lots of products, but there's also lots of reactants. So I need to use up some of those reactants that were added in order to get K to be back where it was. Because K is a constant. I should have the same relationship between products and reactants. And I don't if I added B in. So what ends up happening is when B is added, the value of the equilibrium constant, quote unquote, technically changes for that moment. In fact, we actually give it a new name. It's called Q. But that's a 163 topic that we're not going to really explore in this class. In order to get K back to what it should be, because K will always be the same, it's a constant, the system and all the reactants and products inside will exchange and react or decompose or whatever, such that you get back to the correct value of K. And so this is known as Le Chatelier's principle. If you change the equilibrium conditions, the reaction will adapt and try and revert back to what it was. Now, it may not be possible to get to the exact numbers, but it is possible to get to the same value of K. So let's suppose that I had this. So we know that K is products over reactants. Let's suppose at equilibrium that they equal 50, like we said before, because I had 50 products. I don't know how to spell products, apparently. For every one reactant. And then what I do is I go like this. Haha, now there are no longer one reactant, there are now 100 reactants. So I have changed the equilibrium. So I am no longer equal to 50. In fact, 50 over 100 would be 2, right? But I got to equal 50. So what will happen is that I will turn more reactants into products until I get a ratio that is again 50. And so that would be something like 147 divided by 3. And if you punch that in your calculator, 147 divided by 3, you get 49, which is real close to 50, right? So what would actually happen is I'd get like 147.5 and 2.5, or whatever it is that makes it become 3. So by me doing this, the reaction is driven in the forward direction so that the equilibrium constant once again equals what it was before. So if you flood the system by adding a ton of stuff, the reaction just goes in whatever direction is necessary to undo your change so that it can get back to what number ratio it had for K before. Now, normally I do this standing in front of the class and I hold my hands out like a seesaw and I say, oh, I have too many products, and I tilt in the direction of the products. And then I tilt back towards reactants to indicate, oh, we're making more reactants to balance out the system. But I can't do that because I don't have a webcam that works. So you can't see me going like this in my chair. So instead, we're going to have to do this a little bit just more descriptively. So if you get confused by what I'm talking about, let me know. I'm going to draw lots of pictures here. So let's suppose that I have my system at equilibrium, and then I put more B in. So my system is at equilibrium, and I have some amount of reactants. Oops, I guess I should call these A and B. How I drew this makes no sense, I just realized. Hold on. There we go. It should be, this side should be smaller. Or lower. There we go. So we're at equilibrium. Here's my balance. And so my equilibrium constant is whatever we said it was. And then I'm going to put more B in. So here's what I'm going to do with B. So we've got the original B that was there, and I'm going to put more of it in here. So what would end up happening is this would sink. And I would no longer be pointing at K equals 50. Instead, what would happen is that would look like this. Here's where I should be. Okay, how do I get my reaction to go back to equilibrium? Well, I need to react A and B to form more AB, right? So these two would then react. And what I would end up having at this point now is there'd be a very tiny amount of A. There'd still be a lot of B here, but there would be much more. I drew the scale the wrong way again. There would be much more AB than before. This is hard to draw. And this would keep going until my equilibrium constant was back to what it was. So we started equilibrium, we induce a change, and the change was that we added more B. And then over time, the system will go back to equilibrium by attempting to undo that change, which is what's happening here. Okay, so by adding B, some of the B reacts with the remaining A that's in there to form more AB until the ratio of products is once again 50 to products to reactants is 50. Now, generally speaking, if you add something to your container, the reaction tries to use up what you added. However, there are other actions you can do. You can remove something. If you remove it, the reaction will try to replace what you took out, because if removing something wrecks your equilibrium just as much as adding something, right? So let's look at this reaction. We're going to look at a bunch of scenarios. So in scenario 1, I have ammonia that is produced from the reaction of nitrogen and hydrogen. Now, if the system is at equilibrium and I add ammonia, what happens? So let's look at that. So we're going to just assume that the equilibrium constant is flat here. So we've got N2, we've got H2, and we got NH3. So I'm at equilibrium. Now, if I add additional NH3 up here, so extra, then this side sinks. I have too many products relative to what my K should be, right? And that's no good. So what will the reaction do to fix that? Well, if this is my circumstance that I'm at now, and I want to get back to equilibrium, and I have all this ammonia, then I need to get rid of it so that I can put more stuff over here. So I'm going to decompose to make more reactants. And when I do that, the result that we would get would be, okay, I have more N2, I have more H2, and I have enough NH3, and I'm back at equilibrium again. So the action that occurs here when I've added extra NH3 is I decompose to reactant. So I'm going to use up that NH3 that was added, turning it back into reactants, N2 and H2, to try and undo the change that I induced. All right, let's look at this example. What if I instead removed nitrogen? So we'll clear this, and we'll draw our basic setup again. So we're at equilibrium. And then what I'm going to do is I'm going to remove N2. Well, what happened to my balance? Well, now there's far too few stuff on this side, so this side goes whoop. And I'd be pointing in this direction again, right? So now my balance looks like this. I took out all the H2. I'm no longer at equilibrium because this would be equilibrium. How do I get back to equilibrium? I need to get more stuff on this side, right? So I will decompose my products to form more reactants to try and fill in that gap. So the amount of NH3 I would have would decrease. And the result that I would end up with is I have less NH3. I have more H2. And I make some N2 to try and balance it out. And we reach equilibrium. Now you'll notice that the amount of H2 that I have is more than the amount of N2 because I had some to there to begin with. I didn't remove the H2. I only removed N2. But the ratio of products to reactants will be the same as it was before when it was at equilibrium. So again, what we're doing is we're just trying to undo the change that we are inducing on the system. That's Le Chatelier. Now, in this system, we have gases. Nitrogen and hydrogen are both gases, and so is ammonia. All gases exert pressure. Now, at equilibrium, there is going to be an equilibrium pressure. If I change the pressure, I change equilibrium. Now, an example of this would be if you breathe in oxygen, the oxygen goes into your lungs, but it only goes in so much, right? You don't absorb all the oxygen out of the air. When you exhale, there is some oxygen there. In other words, there is an equilibrium. Some of the oxygen goes into your lungs, and then at the same time, when your lungs get saturated enough, the oxygen goes out of your lungs. When you exhale, there's very little oxygen in your lungs, and so your lungs exchange out better. That's why we inhale air a lot. When you are short of breath or you need oxygen, you just take a deep breath, and then you exhale, and then you take a deep breath, and you do the inhaling part slower because you're trying to get more oxygen. You're trying to maintain the pressure of oxygen in there. If the oxygen pressure is high, you will saturate your lungs better. If the oxygen pressure is low, you do not saturate your lungs as effectively. So pressure obviously affects how this equilibrium relationship works. So what ends up happening here is that if you change the pressure in a system, that will screw up your equilibrium too. And so the equilibrium of the reaction needs to be the same, right? We need to have the same value of the constant. So the system will move in a direction to try and counter the change in the pressure. And what that means is that if I compress a system so that it is very pressurized, I need to reduce that pressure. If I expand a system so that it is in a vacuum, or it has a reduced pressure, I need to fill in that space. We can draw a picture to show that in action here. So I want the pressure of this system to be constant at equilibrium. So whatever it is. And here's my gas particles. Maybe this is my ammonia. Maybe this is my hydrogen. Whatever it is. Now let's say that I compress the system. Now everything is in this space here. And it's very high pressure. What ends up happening is the following. So P is too high. Too high for equilibrium. We need to reduce the pressure. And so what ends up happening is our reaction is going to move in the direction that reduces the pressure. Well, how many moles of gas are on each side of the equation? If I had only reactants, I would have 1 mole of N2 and 3 moles of H2. And we get that from these coefficients here, right? So there are 4 moles of reactants if I had only reactants. If I only had products, though, I would only have 2 moles of products, which has a lower pressure. 4 moles of gas in a container, or 2 moles of gas in a container. You think of this in terms of the ideal gas law. If I put twice the gas in, what happens to the pressure if the volume and temperature are the same? And obviously the pressure has to double too, right? Because there's twice as many particles. So, if my goal is to reduce the pressure, then this reaction will move towards the side with less moles. And in this case, we make more products. So pressure is a case-by-case situation. It depends on the reaction and how many moles there are. So if I compress the system, there is too high of a pressure to be at equilibrium. I have to reduce the pressure. So the reaction moves in the direction that has fewer moles to reduce the pressure. In this case, that's the products. Now let's suppose that we did the opposite. So I'm going to erase. And I'll draw my system again. And here's my initial state. What I'm going to do is I'm going to expand the container. So now it's twice as big. So I have some pressure at equilibrium. Now my pressure is too low for equilibrium. So what do I need to do? I need to increase the pressure to get back to equilibrium, right? How do I do that? Well, the reaction moves in the direction of more moles. And in this case, that would be the reactants, because the reactants have more moles. So what this means is that we can manipulate equilibrium. If I want to force more oxygen into your lungs, I'll just increase the pressure, because then in order to reduce the pressure back to equilibrium, I have to remove that oxygen from your lungs. And the way to remove it, if your lungs are, like, you're holding your breath, or your trachea or bronchial tubes are closed, is to absorb the oxygen into your bloodstream. And so this is the premise by which we manipulate equilibrium to achieve desired effects. If we need to administer more oxygen to you, we supply a large pressure of oxygen, in which case your lungs go, oh, there's too much oxygen. We're not at equilibrium. We need to absorb some of that oxygen to get back at equilibrium. Likewise, you can do this industrially. I want ammonia as a product. How do I force the reaction to produce more product? Well, since there are fewer moles on this side, I would run the reaction at high pressure. I would put N2 and H2, and I would put it in a container, and I'd heat the hell out of it till it's a high pressure. That would drive the reaction in the forward direction and encourage the formation of NH3. So gas pressure affecting equilibrium is a very important concept for both anything that you do in the medical profession that uses gases, and also anything industrially that uses gases, because changing the pressure is a very easy thing to do. You just add more of it, right? Add more oxygen. There's more oxygen pressure in your lungs. So there's our summary. If pressure increases, the reaction moves to the side with fewer moles. Now, how do you increase pressure? You could add more gas, or if we can change the volume of something, which is the example that we're going to typically stick to. If I decrease the volume of the reaction vessel, pressure increases. And in that case, the reaction moves to the side with fewer moles. So up here, that would be this side. But if the pressure decreases because the volume of the reaction vessel increased, we would move to the side with more moles, and that would be this side in this case. Now again, that's going to depend on the reaction. If I give you a different reaction where I have more moles on the product side, then I would be going in a different direction when I compress or expand the chamber. Now, interestingly, what if I had a reaction where both sides had the same number of moles? In this case, pressure would not influence equilibrium, because there's nothing the reaction can do to alleviate the pressure, so there's no noticeable impact on the state of the reaction. So we've already sort of done these examples, so what I'm going to do is I'm going to give you a different example. So this example we've already talked about. I'm going to give you another reaction. So let me clear this off the screen here real quick, just so we can test this concept. So I'm going to give you this reaction here. So this is a very common reaction that is done to explore equilibrium. NO2 likes to dimerize and combine to make N2O4. So both directions are possible here. And let's suppose that I have a container. Here's my container. And I've got my gas particles in here. There's some NO2 and there's some N2O4. And we're at equilibrium. And there's some pressure at equilibrium. So for problem number 1, what happens if I expand the container? So for problem number 1, we're going to do this to it. And I'm not going to draw any dots. I'm going to just I'm going to leave that for you. And then for problem 2, what happens if I compress the container? So for problem 2 here, we're going to make the container like a third of its size. So there's my container. Okay, so what I want you to tell me is which direction does the equilibrium shift in both cases? So for number 1, your train of thought should be, okay, I expanded the container. What happened to the pressure? What do I do to undo that change? Which direction does the equilibrium shift? What do I produce more of, reactants or products? And then do the same for number 2. I'm going to give you like 4 or 5 minutes to think about that. Type your answers in the chat, and we'll go over these together in just a little bit. All right, 1 or 2 more minutes, and we'll go over the answers here. All right, let's go over the answers here. If I can find my pen, where'd it go? There it is. All right, so for situation 1, I have expanded the container. So now I have the same number of particles over twice the space. And that pressure is too low for equilibrium. So I need to increase the pressure. And the way that I would do that is I would shift to products. Because for every 1 mole of reactants I have, I get 2 moles of products. I need to increase the pressure. So I'll move towards the side that has more stuff. So if I expand this container, I should make more NO2. Now if I compress the container, now everything is in this tiny space here. And the pressure is too high for equilibrium. So I need to reduce the pressure. And so I would shift to the reactants in this case, because there are fewer reactants in terms of moles. Now, interestingly, N2O4 is colorless, but NO2 is dark brown. So you can actually see this in action if you have a container that you can compress and expand that has transparent walls. So you can compress it and you could see that it gets darker. Or I'm sorry, you can expand it and see that it gets darker, and you can compress it and see that the color goes away. So this is actually a phenomenon that you can observe. And I don't think I have a video for that. I have a different video that I'm going to show you in a second here. All right. So the last thing that we're going to talk about for Le Chatelier is the use of heat. So heat is something that can be part of a reaction, because we studied exo and endothermic reactions on yesterday's lecture. We talked about how that can be part of your reaction. Now, if I write the reaction like this, where heat is either a product or a reactant, and you change the amount of heat in there, you can disturb equilibrium. So for instance, if I have this reaction and heat is a product, as in I add water to this cobalt tetrachloride ion, heat is released when this happens. Now, what would happen if I put this in a cold bath? So if I removed the heat, then my equilibrium, which we're going to treat my heat as a product. So here's COCl4 2 minus. Here's H2O. There's whatever the hell that is. Here's my HCl. And here's my heat. So this is at equilibrium. If I cool the solution by removing the heat... Oops, let me get rid of that arrow. I don't want that to look like this is the direction. So we'll just go like this. So if I cool the solution, now I have too few products, right? So this side of the seesaw would go up and this side would go down. And I would no longer be at equilibrium. So in order to replace this, I would have to replace the heat, which means the reaction would have to go in this direction. So cooling down the reaction drives the reaction forward because I've removed the heat from it. What if I heated the reaction up? So I put in a boiling water bath. Well, then the reaction should go in the other direction, right? Now, I have color-coded these based on the actual color of what they are. Cobalt tetrachloride is blue, and cobalt hexaqua compound is pink. And so we can see this actually in action here. All right, so let me window capture this. And we should have a video. Oh, wrong dimensions. All right, so what's going to happen in this video? Oh, there we go. That's what's going on. So what's going to happen in this video is we're going to have the solutions that I just talked about. In fact, can I get this on the screen somehow here? I kind of can't. You know what I can do? Hold on, though. So I can go over here. Just so you can see the reaction while this is going on. There we go. And then I'll just capture it again. Sorry, this is a little bit of technical stuff that I have to do here. Okay. So there's both solutions on the screen there. So there's the blue one and the pink one. The pink one is the water one. The blue one is the chloride one. So what we're going to do is we're going to start with the pink one. And we're going to add HCl to it. And so you can see right here on this, up here at the top, if you add HCl, you have too much HCl. The reaction should be driven in the direction of the blue thing. And you can see that it's turning blue as we do that. So adding HCl drives the reaction towards reactants, as shown above us. Now, if you add water to it, which is right here, adding water should drive the reaction to the right, which should turn it pink. And so you can see that happening here too. All right, so this first one, we're going to add HCl again real quick to turn it blue. So again, adding HCl drives the reaction towards reactants. And we have a blue solution. But now what the scientist is going to do, I don't know the gender of the scientist, so I don't want to misgender them. They're going to add silver. And you might think, well, that's not anything in our reaction. But what silver does is it removes chloride. Silver will remove Cl. So if I remove this from the solution, my solution now has to go in this direction to replace it. And so it should turn pink. And you can see that it starts to turn more pink than it was. In this last demo, we're going to put it into a hot bath and a cold bath. So the cold bath is the one on the right. The hot bath is on the left. If I add heat to the reaction, it should... I have too much heat. I got to drive the reaction away from heat, so it should turn blue. And you can see it right there. And then when I put it in the cold bath, that should remove the heat from the equation. I need to replace the heat that's up here. So I'm going to drive the reaction forward, and it'll turn pink. Now, unfortunately, the video cuts out as it's turning pink. But if you look at the very bottom, I'll try and pause it. You can see that at the bottom there, it's starting to turn pink. So it's definitely working, and then the video's over before they really finish, which is unfortunate. Oh, we can get rid of that there. There we go. So, as we saw in that demonstration with Le Chatelier's principle, when you change the system in some way, whether that is by adding a reactant, removing a reactant, adding a product, removing a product, adding or removing heat, or modifying the pressure, the system will just try and undo what it was that you did and go back to equilibrium that way. So I'm going to give you this reaction here. We're going to pretend that CS2 is red. It's actually a colorless liquid. But pretend that it's red, and everything else is clear, and that everything is a gas. So what I want you to do is tell me if you do these things to your solution, what will happen to its appearance? And I want your answers to be more red or less red. Okay? So if you add H2S to the system, which direction does equilibrium move? What color will it turn, more or less red? What if you remove methane? What if you make it cold? So go through these. I'm going to give you like 4 or 5 minutes to do that, and then we'll go over the answers together. And then that's Chapter 9. This is the end of Chapter 9. So I'll see you in a bit. All right, 1 more minute, we'll go over the answers. All right, so let's look at this. Let me clear this screen here. I can't click on the thing. There we go. So we'll do that. All right, so for this first... Oh, what did I just hit? Oh, I maximized the window. Oh, no. No, why? Oh, I broke everything. Oh, no. Okay, well, it still works well enough. I'm just going to have to fix this before the next class. So, okay. So for the first one, if I add more H2S, so I'm at equilibrium, I got CH4, H2S, and then heat. So here's what I have. If I add more of this and make this bigger, then I have too many products. And so my equilibrium will no longer be at equilibrium. It'll tilt like this. So to get it to go back, I need to go towards products. I have too many reactants. Sorry, I go towards products. And since CS2 is a product, this should be more red. Now for the second one, if I remove CH4 here, so if I remove this, now I have too few reactants, and so my equilibrium will be like this. In order to fix this, I have to replace the CH4 that was lost, right? And so the reaction would go in this direction to balance it out. So I'd make more reactants. And so that would become less red because we're using up some of our CS2 to do that. Oh, I need that equation on the board there. Okay. Now, if I make the solution very cold, that'd be like getting rid of the heat, right? Well, heat is a reactant, and so if I have too little of that, I'm no longer at equilibrium. So I need to shift in this direction to replace the heat. So I need to make more, we'll put quotes, reactants, because heat is a reactant. And so this would turn less red. And then finally, if I reduce the volume of the reaction vessel to something that's smaller, so here's my stuff. Now it's in a tinier space because the volume is reduced. Whatever pressure was at equilibrium, now that pressure is too high. for equilibrium. So I need to reduce the pressure. And in order to do that, I need to go to the side with fewer moles. So how many moles do I have here? I need the pen here. So I got 1 plus 2. Heat doesn't have any moles. It's not a gas. So I have 3 moles of reactants, but I have 1 plus 4 is 5 moles of products, which you can't see because it's scrolled off the top there. Well, I need to reduce the pressure, so I'm going to move towards reactants because there are fewer of those, and as a result, this would become less red. There you go. Very good. That's Le Chatelier. So your job is to figure out which direction equilibrium will move. And that's all the time that we have for today, although you do get your dancing work. So hold on, let me get back to here. And there we go. Oops. Oh, there's the homework practice. I got to put that up there too. So there's the homework practice for that last section. I'm going to put the Chapter 9 quiz up later tonight after classes, and not after classes, after I'm done with all my classes tonight. But there we go. Hooray. And that's all I got. So when we come back next week, do know that the schedule is a little bit weird for week 10 as well, because there's an exam at the end of week 10. We're going to have class on Monday and Tuesday. We're going to finish all the content, because Chapter 10 is the last chapter. We're going to finish that on Tuesday. Wednesday is a review session. If I need to finish a little bit of class content, we'll do it on Wednesday, but I expect that we'll be done on Tuesday, and we'll just have a review. And then you have your exam on Friday, and then you have a final a week after. So there are some assignments that will be due coming up. Make sure that you stay on top of those. One of those is due tonight, so that's quiz for Chapter 7. Make sure that you get that done, because it will be closed within a few hours. And then quiz 8 and lab worksheet number 4 are due. They're due tonight, but last call is tomorrow. You'll get an email about that at 5 p.m. tomorrow. But yeah, that's all I got. So otherwise, beyond all the work that we still have left to do, do enjoy your weekend. Make sure that you get out and enjoy the sun. It's too hot for me out there today. So go out there and have fun, but keep studying, and we'll see you next week for the finale.